Alright, so these are the more difficult is probably the wrong word. The reason why they're harder is because it's actually not the derivative that's harder, it's the algebra. Alright, so the first example, again, we always try to make our life a little easier if we can. There's two ways you can take the derivative. I'm going to leave it and do the first way, which again is probably not the way I would go, but you can do it this way. So if you leave it, you'll have the chain rule, and then you have this fraction in this function. So the inside function is x squared divided by 4, natural log. Alright, so the inside is the square divided by 4. Alright, so the derivative, dy over dx, would be 1 over what's inside times the derivative of what's inside. Well, the divide by 4 really is 1/4. So there's a 1/4 that comes along. And then I take the derivative of 2x, which is going to give me, or x squared, which is going to give me 2x. And so there's the derivative, which in essence isn't hard, but then to clean this up sometimes, because it's a complex fraction now. And so to clean this up, which is why this is probably not the way I would go to do the derivative. I'm going to show you a second method that you don't have to do quite as much algebra manipulation. But to clean this up, first of all, this first term is, I would rewrite it, division is the same as multiply by the fraction. So this first term, I can rewrite 1 divided by x squared divided by 4 as 4 over x squared. That's the exact same expression. 1 over, so in this first expression, it changes to 4 divided by x squared. In the second expression here, that 4 will reduce with one of those and leave me with x over 2, right? Because I still have a 2 there. And so I've got 4x squared from the first term, x divided by 2 in the second term, and then I can take that one step further and reduce this down to 2 over x. Alright, that's one way you can solve this derivative, and that's a perfectly fine way to solve it. Now, again, to get to the answer, the derivative is 2 divided by x. You have to do a little algebra manipulation. An alternative to this, which is again probably the way I would go, is you can rewrite this expression using your log rules. First of all, I can get rid of the fraction by rewriting this as the natural log of x squared minus the natural log of 4, right? That's one of our log rules. And then I can get rid of the chain rule, so I can get rid of the divide by part, the fraction, by doing that. And then I can get rid of the chain rule by pulling the 2 out front. Again, I haven't done any derivatives yet. What I've done is I've rewritten my original function in its expanded form, is what we call this. This is the original would be the condensed form. This would be the expanded form. By expanding it, I get rid of the fraction part, and I get rid of the chain rule part. And so when I take the derivative of this, well, the 2 is just going to come along. The derivative of natural log is 1 over x. And this is just a constant, right? The natural log of 4, I can plug into the calculator and it'll spit out an ugly number. It's just like the square root of 2, or pi, right? When I take the derivative of it, there's no x part, and so that zeroes away. And so I'm just left with 2 times 1 over x, which simplifies to 2 over x. So again, either method is fine. The first method a lot of students use because they just start off that way. But sometimes it's easier to manipulate things algebraically a little bit to make the derivative a little nicer, a little easier. So again, you pick your poison in this case and decide which way you want to go. Second example. Again, I'm going to do a little algebra manipulation. If I leave it, I'm going to have to use the chain rule and the quotient rule, because the inside function, you'll notice, is a division. Right? I've got 2x cubed minus x divided by x. But there's a simple algebraic trick you can use to make your life a little easier. I can rewrite the big fraction as 2 little fractions, right? 2x cubed divided by x minus x divided by x. And then simplify. Natural log of 2x to the second minus 1, right? 2x cubed, the x is reduced down to x squared, and then x divided by x is just 1. And so I simplified inside to the expression. I took my original expression, which is a division, and simplified it to a simple function, 2x squared minus 1. Which I can do that, that's fine, as it doesn't change anything because the original expression doesn't allow 0. but the natural log function doesn't allow 0 as well. Alright, so this is a much easier derivative to take. And I can't go any further. I can't distribute the natural log, so I don't think you can. You can't do anything more. That's as simplified as it can get. But I no longer have to use the quotient rule. I still have to use the chain rule, but no longer have to use the quotient rule. So when I take the derivative of this, it's 1 over what's inside times the derivative of what's inside, which is just a 4x. And then if I rewrite that as 4x over 2x squared minus 1, and there's my derivative, which again is not too bad, and I didn't have to use a quotient rule. Alright, the last example is a tricky one because of how it's written, but you do have one of these in your MyLab. Alright, they like these questions in the book. Actually, I think there's a couple of questions where they have them like this. And so what you have to recognize is this is different than what I did earlier. If it had been the natural log of x to the 10th, I can reduce that by pulling the 10 out. But this one's different. You'll notice that the natural log, just to make it a little bigger, is inside x to the 10th. And so this really is a power function, right? If u was my natural log part, that's the inside. And then the outside is the power. And so I have to use my chain rule. Outside power chain, inside logarithm. And so you have to be careful with this. For some reason, this one's hard for students to wrap their brains around. It's just hard for them to see what it is, and they try to simplify it different ways. But the derivative is outside is the power, inside is the natural log. And so when I take the derivative of this, the first thing I do is my power rule. I pull the 10 out, take the expression inside, which stays the natural log of x, raise that to 1 degree less, which is 9. So the power part, 10 times the expression, natural. So remember what this means. This means there's a natural log times itself 10 times. Natural log times natural log times natural log 10 times. When I take the derivative of that first part, it's 10 times the natural log times itself 9 times, but I'm not done yet. Right? I can't stop there. I have to remember the chain rule. Well, now I take the derivative of the inside, which is the natural log, and that's going to be 1 over x. And so the derivative is 10 natural log of x raised to the 9th times the derivative of the natural log, which is 1 over x. And it's fine if you leave it like this. You could write it as a single fraction if you wanted to. Nothing reduces. Up top it would stay 10 times the natural log of x, and you would definitely need parentheses around the natural log of x, all divided by x. So I would actually probably just leave it like this. But if you like to write it as a single fraction, that's how it's single fraction. You can't reduce anything. Nothing simplifies. You can't rewrite anything. Can't put the 10 inside. Right, it has to stay 10 outside parentheses. Natural log of x raised to the 9, where the 9 is outside the parentheses, all over x. Alright, and so again, that's the derivative of that particular function. Alright, like I said, there was one like this I know in your Math Lab, so make sure you understand it. The book typically asks one like this in your My Math Lab. Alright, so that kind of finishes up the more algebraic ones where you have to kind of manipulate things algebraically. And we'll stop there and pick up applications in